So, this lecture is on algorithms for sorting, and the focus of the lecture is going to be not just on the algorithms, but the sequence of steps that go into arguing that the algorithm is indeed correct and analyzing the running time. One of the simplest algorithms to sort a given data set, and in this case we assume that the input is given in an array of size n, that the elements are a of 1 to a of n. The data type of the elements in the array is not so important for the rest of the presentation, as long as it is clear that there is a very clear order between every pair of elements. The output of a sorting algorithm is to sort the array in ascending order, and insertion sort is a very simple and popular algorithm to understand the challenge of sorting. The approach that is taken by insertion sort is the following. It is an iterative approach, which means that there is a loop that is running n times. Recall that n is the number of elements in the array that need to be sorted, and at the end of every iteration, let us say at the end of the ith iteration, the invariant that is maintained by the algorithm is that the elements from the first I elements in the array, that is the elements a of 1 to a of I, are sorted in ascending order. Further, in the ith iteration, the element a of I is inserted into the correct location among the elements a of 1 to a of I minus 1, and thus this invariant is maintained one iteration after another. This kind of guarantees the correctness of the insertion and sort algorithm to sort an array of n elements. Of course, the challenge here is to understand how the insertion happens. Recall that in the previous slide we mentioned that in the ith iteration, the element a of I is inserted into the correct location, so that a of 1 to a of I is sorted. Given that a of 1 to a of I minus 1 is sorted when the control enters the ith iteration. So, how does one insert a of I? One can look at the step by step procedure. We set first j to be a temporary variable, and then if j, whenever j takes the value 1, you exit. Right. We will see what the motivation for this condition is, and as long as j is more than 1, a comparison is made of the elements a of j and a of j minus 1. In other words, the elements which are in the array locations j and j minus 1 are compared, and if a of j is smaller than a of j minus 1, right, then there is an exchange that is effected, right, between the elements in the locations j and j minus 1. Right. And now j is decremented by 1, and then we repeat this procedure all over again. Indeed, it is also possible that the element at the jth location is at least as large as the element at the j minus 1th location, in which case it is clear that a of j is at the correct place, given that the rest of the elements are in sorted order. Right. At this point of time, the control exits, and now we can report that the elements a of 1 to a of I are in sorted order. In other words, we achieved the goal of inserting a of I into the correct position. Let us just look at this pictorially. This is taken from Corman, Lyserson and Rivas, the standard textbook, and let us look at the starting array, which is array indexed by the letter A, and observe that there are 6 elements in this array which start out as 5, 2, 4, 6, 1 and 3. Observe that in the first step, right, in our case this would be the second step, the way I have presented the algorithm, the elements 2 and 5 are exchanged. In the array indexed by the letter B, observe that the first 2 elements are in sorted order, and the element 4 is now being inserted into its correct position, and this just requires a single comparison with 4 and 5, but of course, the comparison with 2 should also happen, therefore, it actually requires 2 comparisons. Similarly, if you look at 6, 6 is larger than 5 and this one comparison keeps 6 exactly where it is, and then observe that 1 is now inserted into the correct position after 4 exchanges. 6 first goes into the is exchanged with 1, then 5 with 1, then the value 4 with 1, and finally, the value 2 is exchanged with 1. Similarly, 3 now is moved to its is inserted into its correct place in the figure indexed by the letter E. At the end of this whole procedure, we find that the array is in sorted order. This is essentially the idea behind the insertion sort, and one can even imagine this as a very natural way of arranging a deck of cards. How does one guarantee the correctness of this insertion sort algorithm? The way to guarantee the correctness of this sorting algorithm is to now argue that in the ith iteration, the element a of I will move to its correct position among the elements a of 1 to a of I minus 1 within I comparisons. Right. In other words, we prove this by induction. Right. We observe that at the end of the ith iteration, the elements a of 1 to a of I minus 1 are sorted in a of I are sorted in ascending order. Right. We prove this by induction on the value of I. Observe that when I is equal to 1, which is the base case, the array just containing a of 1 is just in sorted order. So, let us assume that a of 1 to a of I minus 1 are sorted in ascending order, and let us complete the induction step. So, the hypothesis now is that a of 1 to a of I minus 1 are sorted in ascending order. Now, a of I, let us assume that a of I is now inserted between the elements a of j and a of j plus 1. So, let us look at the indices that j can take. J can take a value between 1 and I minus 2, right, and wherever it is inserted, on termination, it is clear that a of I is at least as large as a of j and a of I is less than or equal to a of j plus 1. Right. In other words, as the algorithm progresses, the prefix of the array which is sorted, its length keeps increasing iteration by iteration. Consequently, at the end of the nth iteration, it is clear that the elements a of 1 to a of n occur in sorted order. Right. Therefore, insertion sort is indeed correct in the sense that it terminates, and on termination the array is in sorted order. The analysis of the running time is based on the observation that for the element a of I to be inserted into its correct location, in the worst case you just need 2 times I minus 1 comparisons. We use comparisons as a measure of the running time, and we count the total number of comparisons that need to be made to ensure that I is inserted into the correct place, and here we place an upper bound. In other words, we do a worst case analysis of the number of comparisons which are required, right. And observe that if the element, the worst case is the case where the element a of I should eventually enter the location a of 1. In other words, in the elements a of 1 to a of I turns out to be the smallest element in this sub array of consecutive elements, then a of I indeed has to be compared, right, with each of the elements, right, that is I minus 1 all the way up to the element indexed at I minus 1 up to the element indexed by y by 1. Further, in each of these iterations, if you notice the code that we have written, there is a comparison of whether the index is equal to 1 or not, right. So, that is why we get 2 into I minus 1 comparisons. Therefore, the total number of comparisons made is one comparison for the first element, and subsequently it is an even number of comparisons up to the nth element, right. Therefore, the total number of comparisons that is made is given by the summation 1 plus 2 plus 4 plus 6 and so on up to 2 times n minus 1. Here is a small exercise which is indeed a toy exercise. Calculate this exactly and verify that it is of the order of n square. So, this brings to end the discussion of insertion sort, and it is instructive to see on what input insertion sort performs the most number of comparisons. This is also left as a small exercise to the student. Natural question now is that can one reduce the number of comparisons made by a sorting algorithm from order of n square to something significantly smaller than n square. We now show an algorithm which uses the divide and conquer paradigm. Recall that in the last lecture where we studied binary search, we encountered the divide and conquer paradigm, where in that case we were searching for a particular element in a sorted array, and in every iteration the region of the array which is sorted became smaller by a fraction of 2. In this case, we do something similar. We create 2 sub problems of almost equal size, sort the 2 sub problems recursively and then merge the sorted arrays. So, this is the whole idea. This is a divide and conquer paradigm, and this is what merge sort does. Right. The sequence of steps are as follows. For the goal of sorting an array whose indices are in the interval p to q, where p is smaller than q. Initially, the first time when merge sort would be called, the value of p would be 1 and q would be n. That is, we want to sort the array of size n. The algorithm takes a middle element in the given array. In this case, it computes the index given by the formula r, which is the floor of p plus q by 2. In other words, the range p plus q is taken, which is the sum of the 2 elements divided by 2 gives the middle index in the array, and we take the floor just in case p plus q is odd. Okay. If r is not same as p, in other words, if the array has more than one element, okay, or more than 3 elements, if the array has more than 3 elements, okay, then merge sort of p comma r is called, followed by a recursive call to merge sort of r plus 1 to q. Observe that here is a boundary condition of what happens when r is equal to p. Observe that when r is equal to p, there are at most 2 elements in the array, right, and there is no need to recursively sort, right, the elements of size 1. Now, the 2 arrays a of p to r and a of r plus 1 to q are now sorted, right, recursively using merge sort itself, at the end of which the array a of p comma r and a of r plus 1 comma q are sorted arrays. We call a function called merge, which we will shortly discuss. The output of merge is to take these 2 sorted arrays and insert them into a third array, which is called B here. B contains both all the elements of both the arrays in sorted in ascending order. Now, B is now copied into the array p comma q, which is now sorted, and this is a description of the recursive algorithm. The natural question now is how many comparisons are made by this merge sort algorithm. Before we go there, let us look at a key step, right, which plays an important role in the merge sort algorithm, which is the time taken to merge two sorted arrays. Right. Let us look at it as an independent exercise, not just in the context of merge sort, but just the question of the input consisting of two sorted arrays and the output should be a third array which contains all the elements of the two arrays in sorted order. This operation is called the merging operation of the two sorted arrays A and B. So, let us look at the time taken to merge the two arrays A and B into a sorted array C. The idea is quite intuitive. So, initially x and y are taken to be 1, they are the smallest elements in the two arrays respectively, and z is the first element, the index of the first element in the array C. Okay. The first step is the following, which is very important. This is the beginning of an iteration. If z exceeds the total number of elements in the array, in the two arrays, then you exit, merge has been completed, you return the value of C, the algorithm returns the value C. In the second step, the smallest of the two elements, second and the third, in the second step the smallest of the two elements A of x and B of y are identified, and the smallest of the two elements is now assigned to be the element present in the array index z in the array C. This is iteratively done, right, as follows. A of x is compared with B of y. The smaller of the two elements, as you can see, is assigned to C of z. Z is then incremented, and depending on where the smaller element came from, whether it came from A or B, the indices x and y are incremented. The indices y and x are incremented. For example, if the smaller element came from the array y, array B, then the element assigned to C of z is B of y, and y is now incremented and z is also incremented. If the smaller element came from the array A, then x and z are incremented and the array element A of x is copied into the array index z in C. Now, we will argue that this indeed merges the two arrays, and we will also count the total number of comparisons made. At this point of time, before we go into that argument, let us just look at the execution of the merge sort algorithm, and again this image is taken from the textbook by Korman, Lyserson and Drivist. And let us look at the run of this algorithm. The leaf levels in this tree tell us the initial array. The initial array has had 8 elements, and the elements are 5, 2, 4, 7, 1, 3, 2 and 6. And observe that in this view, every intermediate array that you see as you view this in a bottom up fashion, right, is a sorted array, and the parent of two arrays is obtained by merging the contents of the two sorted arrays. Let us just look at the leaf level. Let us look at the elements 5 and 2. Individually they are in sorted order and they are merged to result in the parent array which has the elements 2 and 5. If you look at the sibling, the right sibling of the array 2, 5, it is 4, 7, which is obtained by merging the two arrays which have just a single element 4 and 7 respectively. Now, 2, 5 and 4, 7 as you can see is merged to give the array 2, 4, 5 and 7, and eventually the whole sorted sequence is obtained at the root of this recursion tree. It is important to observe that this data structure is present only in the analysis of the algorithm, and the algorithm indeed does not run in this order. It runs in a top down order as opposed to the analysis which is happening or which is being presented in a bottom up fashion. Okay. Let us look at the correctness analysis of the merging step. The merging step is indeed correct. So, let us just observe a primary invariant which says that for every z in the range 1 to L plus m, after the zth iteration, C of z satisfies some nice properties. C of z is smaller than all the values in the array A among the region x to L, among the indices x to L, and it is smaller than all the values in the array B among the indices y to m. Therefore, it follows that C of 1 to z, all the values are at most each value in the array indices x to L in A and the array indices y to m in the array B. The third property that is guaranteed by the algorithm is that the array C is sorted, right, for every z. So, remember that z is the iteration number. To prove the above claim, it is sufficient if we prove the above claim, this proves that the merge algorithm is indeed correct, because when you take the value z is equal to L plus m, the array C of 1 to z would be sorted, that is the whole array is sorted because of the range of values that z takes from 1 to L plus m. Continuing the correctness analysis, we set up the proof by induction. Let us assume that z is equal to 1, and in this case the singleton array, the array containing just one element, is sorted. It is indeed the smallest element in the arrays A and B, right, and therefore, our claim is correct in this base case. Let us assume and let us make the induction hypothesis that the claim is indeed true for a value z minus 1, and let us prove this for z. This would complete the induction step. Right. So, the first claim is that C of z is the smallest element in A of x and among A of x and B of y. This is indeed correct, because if you look at the steps in the algorithm, we choose the minimum of the elements A of x and B of y and assign it into the value C of z, right, and therefore, C of z is indeed the minimum. Since A and B are sorted, it is clear that C of z is indeed smaller than the elements in the array locations x to L in the array A and the elements in the array locations y to m in the array B. By induction, we know that C of z minus 1, right, is indeed smaller than or equal to C of z. In other words, we know that by induction that C of z minus 1 is smaller than or equal to all the elements in the arrays A and B put together, and we have taken the minimum of all those elements and put them into C of z. Therefore, C of z minus 1 is smaller than or equal to C of z. Consequently, it follows that C of 1 to z is in the sorted order, given that C of 1 to z minus 1 was in the sorted order by the induction hypothesis. This proves the induction step, and therefore, we have proved that merge indeed does succeed, that after L plus m iterations, the whole array C is in the sorted order, and therefore, the merge algorithm indeed succeeds. Let us now analyze the running time of merge. It is very important to get an understanding of how much time it takes for merge to run. It is crucial to understand how does one count the running time, and in this case we count the total number of comparisons. The most important observation that we make is that every time a comparison is effected, the size of the array C keeps increasing by exactly 1. As a consequence of this observation, after L plus m comparisons, there will be L plus m elements in the array C, and therefore, the total number of comparisons used is a sum total of the total number of arrays elements in the two arrays A and B. Therefore, the number of comparisons used by the merge algorithm is L plus M. In other words, it is just linear in the size of the number of elements in the two arrays put together. This gives us a handle to analyze the running time of merge sort. Again, here we count the total number of comparisons made by merge sort. Let T of n denote the number of comparisons made by merge sort on an n element array. For the sake of simplicity, just for the argument, let us assume that n is a power of 2 for some value k, that is n is equal to 2 power k. Now, T of n is given by the formula T of n is 2 times T of n by 2 plus n, and T of 2 is just equal to 1. Let us just understand this formula. This is called a recurrence equation, and 2 times T of n by 2 is the number of comparisons on the recursive subproblems, to sort the recursive subproblems. That is, the subproblem consisting of one half of the array and the second subproblem consisting of the second half of the array. The second term, which is n, is the total number of comparisons made by merge, which we just very recently analyzed. A solution to this recurrence equation gives us a solution to the number of comparisons made by the merge sort algorithm, and this will be completed in the next lecture.